I'll start the stream up. I also I forgot to mention to everybody belated Happy New Year, Lunar New Year, if you celebrate. So it seems like a pretty cool thing to celebrate. It's a Zhihong. That's like one of my ideals is to go to China and be there for the Lunar New Year. But we'll see when that happens. We've got a lot of like trips like that. But anyway, enough about that. Any questions about what we just talked about? Fun? Yeah? Good? Cool. I do encourage you to play around with the JAGS code. Change the prior, change parameters and whatnot. Heck, we could probably do that now. What happens if we change? No, you can change values. You know what's going to happen. Just try to see if you can replicate what happens with JAGS. So you know what's going to happen because you have an answer key. Our last class, the class lecture before this, we changed the prior around. And you can see how the EAP and the MAP estimates change. Standard deviation changes. So you can compare what you're doing with JAGS to what you're getting from like theoretical result, right? This is one of the few chances that you're going to be able to get that because as we get into bigger and better, we're not going to have models that work like this anymore. Okay. Then what I'm going to do is I'm going to move on to the next, what happened here? Documents, repos. We're going to go to the next lecture here, which is chapter 3. I'm going to breeze through this because conceptual issues, I shouldn't say that, but you know what I'm talking about. I think the big issue in this is I built this sort of as I started reading it and I'm like, yeah, but, and oh yeah, but, and so it's the idea when you're reading a book, you're sort of getting the motivation for the book, the motivation for the method, in addition to like the actual method itself. So I was trying to like have pro and con arguments in some of these things as I went through, and I wasn't just taking a contrary version to the book. It was like, yeah, but this, and then someone else said it. So I'm just trying to play two sides of an argument. I think I've been on both sides at one point or another in various discussions. So it's just trying to get out there what's out there. The reality of it is Bayesian inference is not, is really not, it's been around a long time, but it's not really popular in social or educational sciences as popular as the frequentist approaches still. I mean, it's much better than it's been 10 years ago and 20 years ago, but we're still overcoming some of the hurdles. And so I think just knowing what those hurdles are, if you're going to go do a paper in Bayesian with a Bayesian method, I think it would be helpful. I think that's where I got with this. So basically, these are the concepts that reappear in Bayesian inference, and then sort of where they differ from ML. And some of these we've already talked about, sort of my rambling consciousness stream of blah, blah, when I'm up here, how that works. That's me talking, by the way, blah, blah. When I used to have Huey, my son, whenever I told him what I did at work, I said, "It's blah, blah, blah all day." So I had a ringtone that was blah, blah, blah. And he says, "Oh, blah, blah, blah." So I had that on my ringtone, and I had it with my text message. And I always made a point of, like, I was doing, like, low-level administration. I was associate chair for my last place. And I'd be in meetings with the administrative council where all the department chairs and the dean was, and I'd have the phone with the ringer on. And it was always when the dean would start rambling and someone would text me and it'd go, blah, blah, blah. Exactly.
Did they ever get the point?
No, they were frustrated that I would leave my ringer on. But I kind of, like, just, yeah. And you could do the same to me. That's what I'm saying. Incoherent streams of rambling, blah, blah, blah. Try not to take myself too seriously. Okay, so issue number 1, influence of data versus influence of prior. That's a big issue. Never easy to really go with. The main thing to think about, though, is if the prior is just one piece of information, and if you have lots of data, and where lots of data happen to be depends on how many parameters are in your model, effectively, how complex your model is. The data almost always overwhelm the prior. When you're coming from a non-Bayesian perspective, and you're working with large sample things, particularly in measurement, we have large scale assessment, right? Large sample things. The prior has very, very little impact in general in those cases. So It's not a big issue if you come at it from that perspective. It is a much bigger issue if you think about coming from kind of if you're like in agricultural statistics. Anyone ever talk about them here? Is that Iowa State? Is that where it works?
He's mentioned it once.
Yeah, I mean, like a lot of stat, grew out of agriculture. In Kansas, University of Kansas didn't have a stat department, believe it or not, but K-State did, and it was very heavily agriculture-based. They used to have a symposium every year of applied statistics in agriculture. I went one time. I was sitting next to a guy from Monsanto. It was awesome. What do you do? Oh, I do educational measurement. What? What are you doing here? Yeah, exactly. But it was because the method's the same. Anyway, if you look at the textbooks, what I'm talking about are the textbooks that motivated kind of when you got into mixed models and sort of why residual maximum likelihood showed up. It was because there's bias in mixed models in ML for the variance components. And when that happens, it's usually when the small sample sizes happen. If you come at it from that perspective rather than coming from the measurement perspective, then priors can make a big difference. So I think that's what you have to think about. One way to check the sensitivity of the prior is to try to make it less sensitive or change the values of it and see how much the final point estimates of your parameters change. So that's another way of putting it. In our next lecture, it was like yesterday at lunch, I was like, I'm reading about, I'm looking at like 7 or 8 sources for Bayesian linear models. I'm trying to be complete, and each of them is sort of like, yeah, the prior for the variance. It's so easy. Oh, look at that. All you need is your expected, pseudo sample size, which is really degrees of freedom total. And you just need some estimate of your variance of error. A residual variance. Oh, what is your estimate of residual variance? Like, where would you get that from? Like, that's the thing. It's like, let me just go to the store and grab one. I don't... How do you determine what that happens to be a priori is what I got to. So that's where I'm sort of at. I think that comes under issue number 2, motivating the selection of prior distributions. But even then, within prior distributions, what are you selecting for the parameters, right? It relates to how strong the prior is. I tend to think the most benign priors are the uninformative ones. There is a contingent of Bayesian people out there who really like to yell at me for that. You should really have informed priors. I don't know where they're getting their informed priors, but I'm not paying attention to those same sources. So it's just really hard. And what you end up seeing, what you can understand is that priors are quantifying uncertainty about parameters. But in a sense, isn't that why you're doing the analysis in the first place? Right? Oh, gosh, I'm really uncertain about this. Let me run a model and see what it happens to be, right? So there's sort of that blend of the two. Flexible priors seem better than inflexible ones. I like that. Beta, for instance, subsumes the uniform distribution. It's harder, though, to pick priors from previous research because lots of things may be different. Sample, study, right? I guess if you're doing it as direct replication, maybe.
Definitions of the thing you are studying.
Exactly. Yeah. Exactly. Yeah. All the stuff that would go with there. But then you start to see this show up in a lot of the stat text. Experts. We do this in measurement too, right? Content experts.
Tell you what, SMEs don't really know anything.
Subject matter experts, right?
SMEs don't really know anything. You call us experts, mm-hmm. Like I can make you a good item, man. Like.
So that's so is that your role? Is that what you typically do? So I'm not saying experts don't know anything.
Right. I am.
I think expertise is good. The question, though, is can an expert go and give you the information about the prior you need to parameterize it? That's really hard, right? But what you end up seeing, and I'm sort of mocking us because I've been guilty of this before, too. Let me just mock me. Don't point my finger at any of you. But experts is what you write in a stat book when you're saying, not my department. Yeah, I don't know. Someone else does. Go ask someone else. Actually, I don't know. Someone else might. Just ask them. And I'm going to leave that alone. Is that? Dr. Aloe, you're about to undergo a book. Are you going to have experts in your book? Describe that. No. Just remember this. When writing your book, experts. I used to work in retail, and experts is essentially where people would come up to me and be like, hey, do you have more of this in the back? Because it's this question that I've asked many times, and I probably continue to ask, but it's like as if the back of the store that nobody can see is this like Amazon, what we think of Amazon right now, right? This supply warehouse that goes wherever. Let me go check. Oh yeah, there's more in the back.
There might be, but you have no idea where it's at.
That's also possibly true. So anyway, I say that. Experts is where I'm just saying it's sort of a catch-all for, I don't know, someone else might. I can't say that they won't. But oftentimes experts' opinions are very difficult, particularly when I mentioned the judgment decision-making task last time. I'm like, which is farther, San Jose or Key West? That's a hard task, but that's quantifying uncertainty. And that's of a probability. It gets a lot harder when it comes to putting that into a model parameter. Right? Think about the prior distribution for your error variance your residual variance in a linear model. That's a fairly simple model too, right? We take those models way back, like almost in the first class we're in regression at some point, or ANOVA regression, that type of stuff. Good luck, right? Next, Bayesian versus ML. The pro-ML camp says priors are somewhat or possibly entirely subjective. The counter to that is data overwhelmed the prior. Counterpart 2, choice of a model is a prior in some respects. Yeah, that's true. Pro-Bayes, ML is hard. It's difficult to calculate. I don't really agree with that because a lot of the Bayesian techniques are just as hard. Like if you think of like when you're doing ML and you have to do an optimization routine like a Newton-Raphson, yeah, you got to get derivatives and so forth. That's hard. If you're coding though, let's imagine you're not good at calculus, and I'd put myself in that camp. I don't do calculus every day. It's in there somewhere, and maybe it comes back, but it's very inefficient at best. But I do know in coding, if you want to go and find a maximum of an algorithm, there are ways that you can do finite versions of these derivatives, Hessians, gradients.
I would actually say with modern numeric analysis techniques, ML is maybe even easier than a lot of the Bayes estimations.
And it's funny because ML might be actually more computationally intensive even too. So I've heard that, actually it's written that ML is hard, but it's not, I don't think it's any different than Bayes anymore. We've talked about all this other stuff as well. Exchangeability is an issue, but it shows up in almost every, it's written in the context of Bayes here in this chapter 3, but it shows up everywhere. It's exchangeable. It means that I can go and I can think of my observations as counting the same. In our last example, we had 10 trials, 7 of which were successes, and we just lumped them all into the same thing. And by being exchangeable, we could say each of those were independent, right? That was sort of the key. Exchangeability is sort of the thought and how that works. It backs into, what is it, De Finetti's theorem, which it is very important theorem in statistics that talks about conditional independence. But I think there's sort of 2 avenues to where it goes, I think practically speaking, but it doesn't just apply in Bayes. One of the avenues is practical, which is basically, have you controlled for everything that you need to control for to allow for this conditional independence to be there? Because if you omit a variable, you're basically saying I can't exchange my cases. These cases over here are different than these cases over here. Now maybe within these groups they're exchangeable. That would be like ANOVA, for instance, missing factor in ANOVA. The other part where conditional independence, if you can establish it, where it really benefits us is in computation. Because anything that's independent means we can divide in a likelihood, and we can go and put on multiple processors, and we can make highly numeric techniques go faster. So a lot of what we do in analysis, now we haven't seen a model like that yet, but in psychometrics, if you think of what's exchangeable in psychometrics, you have an IRT model, what's exchangeable there? People. People are thought to be the same. Just a simple, basic IRT model. When you get into some of the diff things, you might think differently. But so what that means is if we build a Bayesian algorithm when we're starting to sample people parameters, the latent variables, we can make those independent. We can line them up. If we had a processor per person that would go really fast, there would be no queue for how to calculate that, right? Same thing with items. Typically, in a basic IRT model, you say items are conditionally independent given the value of the trait. Okay, now when we get to the item step, we can calculate things for items separately as well. Independence means separation. And you'll see that a lot in moving from theoretical quantities to numeric estimation of algorithms, is that like the independence features of it, or you can make things independent, make things go much faster, sometimes even more stable. So that shows up. If you're just using JAGs, though, it'll do it for you. So that's good too. Anyway, I'm again fast forwarding through this chapter. It's nice. It's okay, but I want to get to the next topic. So basically, the conceptualizations are sort of where they end, and they talk about there's many ways of looking at how to look at Bayes. What is Bayes, apart from just being a posterior distribution? And I just jotted these down because just kind of keep in your mind that each of these are possibly applicable. They're all applicable. Bayes is a way of updating your beliefs. A posterior is now your version of uncertainty. Right? You start off with prior. I believe this is what prior says. I'm going to go grab data, and now I'm going to go look at posterior and say, oh, you know what? Prior was off a little bit. Now here's posterior. And there's no better place to look at that than our beta binomial example we just had. We had prior, right? Belief, if you want to quantify it, was what we picked those hyperparameters to be. We said they were 1, 1, right? When we add the posterior to it, the alpha parameter was really now the number of successes plus whatever alpha was in prior. So it'd be 8, right? So it went from beta 1, 1 to beta 8, and then the beta was number of failures, really, plus whatever the prior was before, so it'd be 8, 5. So we went from flatline beta 1, 1 to beta 8, 5. That's a belief update. That's how Bayes is thought to be. And the same thing would happen if you would think about, even with posteriors that we can't summarize, like by saying, by looking directly with the conjugate prior, what happens to the posterior, what the posterior shape is, the same thing happens. The posterior is now the update of the belief. And then you can think of, I mentioned 538, the website 538 last week as an example. Okay, so now my belief is what the posterior is. But then maybe I want to go and add more data to it. All right, so that posterior is a prior for the next round, right? And that may go further and further and further. So that's Bayesian updating is a great way of talking about it. Then actually the bugs code is Bayesian updating through Gibbs sampling is what it stands for. So update is one of those. The other top about is taking priors to augment information that's present in the data. So basically blending your belief with evidence. Another way of looking at it is your joint distribution of data is sort of your consistent way of looking at your model. What I'm talking about. The model is sort of the specification. It's just the same thing as ML. And then finally, another way is talking about kind of model building expansion. I guess I could have put exploration in there. In that, a lot of Bayes involves an iterative process in looking at the same data. Whether that's changing your model, whether that's changing your prior, whether that's changing other parts to it, it's an approach that moves forward. So. That was a flyby of chapter 3. I spent an hour on the basic JAGS code. And chapter 3, yeah, that's important stuff. It's a good chapter to read. It's a kind of a good foundation. But the focus I'm trying to lie on this class is an applied one. It is more on the let's just do it and then deal with the nuances of it, because it's harder to see that without that applied basis, I feel like. Any thoughts or questions? Boom. Done. Next, let me check the YouTube. Nope, no questions. All right. Now, next one, I have in this folder called Intro to MCMC, which really shouldn't, that's really not appropriate. It's more become Bayesian little linear models. The book. I'm going to clear my environment here to kind of get back to ground zero, this starting point. The book itself is has a lot of information in it in chapters 4, 5, and 6. But when I looked at it, chapter 4 talks about normal distribution models, and chapter 6 talks about linear models. Well, normal distribution models, when in chapter 4, I said, well, let's go estimate the sample mean, let's estimate the sample variance. That is a linear model where your only parameter is the intercept. So I kind of look at those as a way to generalize. So I'm sort of smushing chapters 4 and 6 together, and then I'm sprinkling in 5. So this lecture right here is really an introduction to Bayesian linear models, which could be chapter 6, but it relies a little bit on chapter 4, and a little bit about chapter 5, because I'm going to go do it numerically here. And then next week we're going to get into a little bit more of the math. I have to give you some of the math. I've heard people comment that a lot of times you take this type of class in stat department, you're deriving what conjugate priors are, right? Posterior distributions are. We're going to do that just a little bit next class just to show it again, but that's only me because I want to talk about matrix algebra with linear models. I think that helps. A lot of times, at least when I was in grad school, this is also me getting to know you as well too. This is the getting to know me phase because in this, I'm going to start talking about a linear model. I'm going to have questions for you. How would you model these data? How would you analyze them? What would you do about that in your what you've learned at this point? Not Bayes, but in what you've learned at this point. And now let's map that onto Bayes and see what we can go. But I'll be able to learn about you from it. I'll also get to understand a bit about you with the matrices as well. And I say that because a lot of times in the graduate curricula in not stat, but in things that are heavily math oriented, applied math, I guess you could probably call us. You'll take classes where there'll be matrices, but oftentimes you won't really work in them after that, right? Depends on who you are, depends on what your research is. And so I want to keep you thinking about them because they're actually really helpful in linear models if you ever get a chance to do anything in linear models.
I don't think our program actually takes it from that perspective often.
So could you elaborate on that?
Yeah, so all the stuff we've been doing with our analyses, you take design of experiments, there's all that matrix algebra there, but we never pull that hood and see what the matrices are doing or how you derive the least squares estimate from the matrices. Our program doesn't really show that.
Okay, well that's good. Well, I can put that in. I have I had sort of just allowed that to be taken for granted, but I can actually go and put that in. But then really I was going to talk about combining posterior and data and prior with matrices as well, but that relies on that as well. And the part of it that's interesting is the in linear models, like once you start reading the matrices for it, like if you go back to some of the great textbooks that are out there, if you look at Remmel, anyone know about residual maximum likelihood? Anyone learn about that? You ever talked about that in your classes?
We talk about it, but we never learned it systematically.
Okay, so like there's a number of papers where sort of Remmel came about, but there's one by a guy named Harville who was at Iowa State in the 1970s, 1974. He has several of them that it's like 3 pages long. It's like the whole thing in 3 pages. And it's so hard to unpack, but you see that when you dive into linear models because there's so many regular matrix forms that show up, something called have you heard of the annihilator matrix or the hat matrix? These are things that just start showing up and you start taking for granted. So when you get into any bit of the linear models at all, like even just for this, they're there, and it's sort of all those jumps that have to happen are there because of it. So I was hoping to put that in there for that reason. It's not going to be sufficient most likely, and it's really rusty. But the other part of that though is that when you start to understand linear models in that way, then you start to understand that factor analysis works the same way very much too. Right, and then you get the cross connection of a linear model and factor analysis. What are they doing the same way? And I think that serves a great foundation for what you do in other measurement techniques. Because if you can understand how you do analyses with observed data, if you could observe people's latent variables, then that really makes a very big difference, I think, in your head about how your latent variable models might look and how they should work as well too. Anyway, I'll leave it there. That's my bent. I want to let to know you. That doesn't mean I might be way off course on this. All right. So in this example here, we're going to have several packages we need. Inverse gamma ggplot2. I'm still trying to learn ggplot. I'm a base R guy because that's where I grew up. How many of you use ggplot? The tidyverse? That's it. I'm trying to catch up with you guys. It looks great. It really does. And I'm not trying to knock it. I'm just, it's a better way of doing things. I'm just slow to get it. And this, again, we're built this off of chapters 4 and 6 with a little bit of chapter 5. So I'm deviating from the text here. In general, I'll probably start to deviate a lot more from the text as we start going on. And it's not a knock on what the text gives you. I think it's the difference in my perspective in the text. And actually, I really do like most of the text. I don't have any strong disagreement with the authors at all, and I actually do respect them quite a bit. It's just my way of talking about it. So don't take that to think otherwise. Okay, Markov Chain Monte Carlo, we just saw that with the beta binomial distribution. In general, the nice thing that we've gotten to this point is that likelihood, the distributions that you have in the likelihood function, the model likelihood, the conditional distribution of the data given the parameters, that term that's on the first term on the right-hand side of the proportional to in Bayes' theorem. When you have data that come from when you say a model and you say that it's part of an exponential family of distributions, are you familiar with exponential family? Okay, exponential family being a very certain form of distributions that we have. Most of those exponential family, and I want to say all, but I'm probably wrong in some case, but they have conjugate priors. So there's ways of picking a prior that should move forward in the distribution that you're working with. And a conjugate prior is not a necessity, though. A conjugate prior is only a nice thing to have because it helps make efficient simulation when we're done. But even then, and we're going to see this in linear regression here, even with the conjugate prior, there are many cases where you can't just go and take the posterior like we did with beta and say, oh, the new beta alpha is this and the posterior beta is this. In linear regression that we're going to see here, the linear model, we have a conjugate prior possible for the variance, residual variance, and our regression coefficients, but you still have to estimate using Markov Chain Monte Carlo because the prior and the part for the betas are conditional on the value of the residual variance. So you would still have to have some type of either numeric algorithm or otherwise, in their case, sampling algorithm that goes and samples the variance and then samples the betas in each step because they're conditional, and they'll jointly converge to where the posterior should be for each. So I think that's part of where we get. As I mentioned before, like the rest of the class is going to be MC for doing Bayes, right? But just don't forget that MC is not the only way to do Bayes, right? You can still do Bayes the same way that you did a lot of maximum likelihood. You can still search the posterior distribution for its mode using Newton-Raphson or using whatever computational techniques that you need. Numerics. Newton-Raphson is just one of many different optimization techniques to do that. The problem with each of those, as we're going to get into the latent variables, is that when you have high dimensional problems, in that I mean you may have multiple latent variables, multiple things that you have to integrate over to get it, if you have to marginalize a likelihood, the bigger the number of things you have to marginalize over to get to your likelihood, the slower it takes computationally. And so what you'll end up seeing is if you had a plot of number of computational steps by how many dimensions you had to marginalize over to get to your marginal likelihood function, right? It's like integrate out theta, right? So number of thetas versus time. Bayes is kind of a straight line. It increases, but it's not. It's a linear increase. Whereas in most of the like the Newton-Raphson or the ways that we go in if we have to numerically integrate out, it's a curvilinear. It's an exponential, really. Every time you add a latent variable, now you've got another set of another dimension you have to integrate over. So if you had one dimension and maybe you had 15 quadrature points to use before, now if you've got two dimensions, it's 15 times 15, right? And then if you get 3, it's 15 times, it's a cube, right? So you have all sorts of stuff that you have to do to calculate to make things work. Okay, questions, thoughts, comments? Is it still true? Question from the audience. Is it still true if the exponential family has random effects or latent variables? It is sometimes true. So the question I think Lisa was asking was when I was saying that most of the exponential family have some type of conjugate prior. And the answer is when you don't have latent variables, yes. When you do, it's sometimes true. It's not always true. And what do I mean by that? You can show a conjugate family very easily in a multi-level model. You can show, so with a multi-level model, you've got normal or Gaussian errors, Gaussian random effects, Gaussian data. You put all that together, you can get a Gaussian distribution out of it if you wanted to make that work. You still have to do an iterative algorithm, but it would be priors on each of these would make it work. In some IRT models, depending on, yes, it's conjugate. If the prior is normal and the posterior is normal, it's conjugate. It's a little more complicated in the linear model, the mixed model case, because the posterior is actually a combination of normal and something about the variance, and that's what makes it harder. The factor analysis is very similar, but more, and then you can do conjugate priors with IRT, but you have to do things a little bit weirder. There's a data augmentation approach that you use, where basically you simulate data for every binary observation. Let's imagine you have a binary IRT model or a binary multi-level model, binary data in general. All right, so binary data, we want to use a Bernoulli for that. Well, there's no real easy prior you can pair with a Bernoulli to make it do anything that's other than beta. And it's really hard when you go and take that probability and parse it into something, with the link function to go and specify what it is. But there is a way you can do it, and it's effectively by saying, okay, for every piece of data I have, for everything that's binary, I'm going to go convert that to something continuous. That's sort of using a trick. In a normal ogive IRT model, effectively you're saying, oh, I've got a continuous normal variable here, and if it's above a threshold, it would be a 1 versus a 0. Then you go and do things with it that would be conjugate. So there's certain steps you can take to shortcut it in more complicated models. But even then, though, that shortcut would still need you to have some type of optimization or sampling algorithm to go and get data from. But it's a heck of a lot more efficient, I will tell you that much. So anyway, conjugate prior. Remember, conjugate, that means type of posterior is equivalent to, type of prior, family of prior, distribution of prior is equal to distribution of posterior. Not the same parameters, right? The hyperparameters of the prior are now updated in the posterior, but the same family, normal and normal. The beta binomial combination leads to beta posterior, so the beta prior gives you a beta posterior. But the numbers change, right? So the shape went from, in our last example, we had a beta prior that was flat, and then all of a sudden it became curved as a posterior. That was sort of the deal. So again, conjugate priors are not necessary to do analyses. They're not, right? And all of the algorithms that you see, all of the, if you go into the JAGS language a little bit, you'll see all the samplers they have are built to make your life go faster and more efficiently when you don't have conjugate priors. But that being said, they are really efficient, and there's something to be said for that. And a lot of the times you can find ways of phrasing conjugate priors that are uninformative. We saw that with the uniform that we saw before. Hope that answered the question. Okay. Markov Chain Monte Carlo. Generally speaking, well, let me go through my notes here. They iteratively sample from the posterior distribution. You've seen this already. We've seen these examples of it, built it with JAGS. For fairly simplistic models, such as what we just ran with our trying to get that probability from the beta. Each iteration is an independent sample, effectively, right? Because if we knew what the beta distribution should be, we can build our own Gibbs sampler from it. We can use the R beta function in R and build a Markov chain, where iteration 1 has very little bearing on iteration 2 or no bearing on it, right? And then our next class, I'm going to show you Markov chain for what we just are doing here to get you to understand what Gibbs is doing or what Metropolis is doing, generally speaking. Because those are, you can see what's dependent on each. For more complicated models, there's some layers of dependency in the algorithm. We're going to see that today. I mentioned it just a second ago, but for the linear model, we need to, when we're going and doing an iteration, remember, in an iteration of Markov chain, each of the parameters has a chance to change its value. Well, in that iteration, we can break it into 2 steps that are dependent on each other. We can sample the sigma squared first, but that's conditional on all the betas being there from the previous step. So there's a layer of dependency, right? So we grab a new sigma squared, and we can go sample the betas second. And those betas, we can do it all from a multivariate normal if we pick the right prior. Those betas now are conditional on the value of sigma squared we just sampled in that iteration. So the difference between the two is that even though we have conjugate priors, our model became more complex where we have layers of dependency that are there. We cannot express a posterior distribution of beta that's independent of sigma squared. So that's where we're after. So that means it slows things down because now you have these, if you think of the train of the algorithm, the way it's working, right? You've got this independent means effectively you could just take each of those steps and run them on a separate processor, or on separate computers and just merge the data back. But when you have a dependency in your step, now all of a sudden, wait a minute, I need to go and chain all of these together. So the iteration 1, sample sigma squared, sample betas. That's an order. I can't separate those. I need sigma squared before I do betas. Now in iteration 2, I need the beta, to do sigma squared for iteration 2, I need the betas from the previous step. They're chained together where I can't separate them. So that's where it slows things down. Even with a conjugate prior, it makes the math a little bit more dependent. Any questions on this? No questions. Okay. As I drink. There are very, very many numerous versions of sampling, of algorithms that we have. I mean, they're just all over the place. They're things that you would never call that way. Like, what is it? But generally, they fall under 2 big types. There's the direct sampling ones, which means you can phrase the posterior in a way where even if it's dependent, you can just draw from it. Right? So given a sigma squared, I know what my posterior for beta should be. I'm just going to go sample directly from that. But then there's the indirect way, which says, okay, I have no real good idea what the posterior distribution is. But I know the distribution of my data, and I know the distribution of my likelihood. And if I come up with some other distribution to propose a brand new value, I can use a stochastic kind of a rejection approach to move along to eventually get to the posterior. So that first way is what we would often call something like Gibbs sampling is what we often call it. It's sort of a direct sample from the posterior. That second way is what we would call a rejection sampling, sometimes rejection-based sampling. Maybe that's the word I call it. I probably shouldn't always call it that, but yeah.
You might not know this offhand, but do you know of a good resource that shows the proof that the indirect sampling Markov chain has to converge?
I don't, but I can look it up for you. Yeah, be happy to. If I don't get back to you, could you send me an email about it? Please do, yeah. I know my limitations are increasing every day, so by the time I shut my computer today, I'll be like, I'm done, okay. But no, I'd like to show it. There is a proof. There is a proof that says, yes, this in the long run, there's actually quite a few that go into talk about how it works. But those are the 2 big camps. And even when you get the new methods that come out, and I say 2 big camps because it's impossible for me to know for certain whether I've sampled the entire literature of algorithms out there. There may be other camp out there that I'm not even aware of yet. But these 2 big camps, are what we often see when we go and do, practically speaking, stuff in JAGs or stuff in SAS or M plus or wherever we go to do most of our measurement-based sampling. Even the new stuff like STAN, it's relatively new. The theory for it's been around since the 1980s. It uses Hamiltonian. I mentioned the Hamiltonian Monte Carlo, but it's effectively this indirect, sometimes we call it Metropolis Hastings, with a really good way of picking a new value or a proposed value for where you may jump. So it moves along pretty quickly, but it's still on one of those camps. So the key, why there are so many algorithms, is efficiency. Again, efficiency means how quickly the algorithm converges. Because what you'll find is for complicated models is you may have a very long burn-in period that you need to run until you start to see the chains stabilize and lie on top of each other like we saw at the Lindenberg plot the last time. So each of the Metropolis Hastings, it's been around forever, and yet for complicated models it's wholly unsatisfactory because you're looking at it going, oh my goodness, is it ever going to end? If you could watch the chain in real time, you'd be like, come on now, you can get there. You can get there, right? And then something else will happen, or it'll have some big shock to the system. It'll go back and then have to go back. Anyway, so it's a long, long process. So efficiency is why we have so many. And the other part of it is there's no one algorithm that works most efficiently for every single model that's out there. And so I was mentioning the case of the data augmentation. Up until, this was not too long after, long ago in the big picture, but in the mid-90s, with logistic regression, people were showing how to build this. There was an article by Albert and Shiv that talked about how to do the data augmentation and all of a sudden enabling Gibbs sampling rather than Metropolis Hastings, right? And that only works for those binary data, or in their case, they actually had it for discrete categorical, something with a countably many number, something where you use a multinomial distribution to describe it. So that's a small part of it. It's really efficient, but only for those little tiny distributions in those types of cases. More often what you end up seeing is that you're going to blend both of these together quite a bit. So there'll be parts of algorithms, if you're really trying to make it go efficiently. If you're trying to do this, let's imagine you had an operational testing program that was based on Bayes. Like, first of all, the steps to implement that, I think we have them, but we don't see them in practice because it's really hard to do. But you need to build something really efficient to give numbers that quick, because you can't be like, scores, it didn't converge. We're going to wait till it converges, and then you'll get your score. Just hold on.
We'll get you back in a moment.
We're going to let this thing. We got auto JAGs. It's okay. All right.
Knowledge isn't important.
It's okay. Give them this. It's coming. Here's our sketch so far. That's right. You can't do that. So often you'd want to build an algorithm that has some type of blend of these. Right. So the parts that you can directly sample from go faster. That will speed up things much quicker if you can't sample from, if you have to indirectly do the other ones. So, and we haven't gotten into the weeds of it yet, but this is sort of the big picture. The good news is that many of these packages and programs keep the choice of algorithm from you. I think that's a blessing if you don't want to know anything about algorithms, but I think a lot of times for me, it was always, I needed to know the algorithm, because if you're coming up with something new, there's usually a faster way of doing it if you're doing it yourself in your own code. Right? So JAGs, M+, they don't make you choose which algorithm to use. SAS even has a few. But you also find, though, that selection that they're doing is very, the algorithm they use is very, very, very hardwired. Right? So if something deviates even slightly when it shouldn't, like in SAS, you can see this pretty quickly. If you should have conjugate prior, you can have it output what it's doing, and it should be Gibbs sampling, but there may be some catches to it where you may have tricked a parameterization. It won't know the catch then, and it's like, well, no, I'm not going to bump you over to the slow one, because the slow one always works for the most part. But you don't have to think about it. It just means that you may take a long time to reach convergence. So, how many of you think you'd ever build your own algorithm? No? Not something you want to do? It's power, though. Nobody can tell you what you can and can't do. No, it's actually come in handy for me a number of times. When you start to come up with something new, not often does it work in this, or not often will it work in an efficient manner in this, in the current framework that you have. So that being said, so it sounds like there's big differences. Generally speaking, those big differences go away in practice because you write code, something else picks an algorithm for you, you get a chain back. And once you get the chain back, you still do the same thing. You're not changing your behavior on writing the code for the model or the prior. You're not changing your behavior on what you do for the output for the posterior distribution. So a lot of times we minimize what's going on in the algorithm. I think that's the fun part, but that's, minimized often for the user. So what we need to have is a burn-in period show up. That's very common in the chain. We need to specify that, even with direct sampling, Gibbs sampling. We also need to have some type of method to assess the posterior distribution. We talked about the Gelman and Rubin if we have multiple chains. There's other ones for multiple chains as well. I'm just going to focus on Gelman and Rubin, mainly because it's everywhere. You see it. It's very easy to use. And then summaries. How do we once we've established that our chains have converged, how do we summarize that posterior distribution shows up as well? Now, there's one additional step that shows up in the rejection-based sampling that doesn't show up in the direct sampling, and that's the tuning or the adaptation that shows up. If you get Stan to install and you run it, it'll say, I think it says warm up, something along those lines. That is effectively trying to tweak the specs of the algorithm to make it efficient when it actually does get recorded. And we saw that with ADAP before. Okay, so we're gonna talk about data now. I'm just gonna jump into data, and this is sort of getting to know each other phase, right? Because I can look in your catalog and see what you've taken. I can see your transcript, but each program sort of has a different focus on different things. This helps me understand where you're at with data when it comes to linear models. It's a very not difficult linear model, but it's something to start with. I borrowed an example from UCLA because I thought they were awesome. There we go. And they are awesome. The UCLA, the IDRE, Institute for Digital Research and Education. Please God, no. Uh-oh, what did I say? Lisa, if you're listening, what was please God no to? Anyway, borrow this example when she catches up and she types, we'll figure this out. I know. Now I might be a little bit worried. Anyway, it was by building your own algorithm. Okay. Whew. I thought it might be don't use UCLA's data. Please, God, no. Okay. Deep breath. Get it back on track here. Okay. I borrowed a data set. I was looking for example data that we could do a specific type of linear model. I wanted to have some type of categorical independent variables and some type of continuous one. We can put it together. Turns out, I found the data, it had all the specs. I should have run it first because like the R square, 0.97. Or, we're explaining 97% of the variance, which makes me think this is simulated data, which I could have done that. I wanted the story. Anyway, here's the data. There's a data file in the folder called dietdata.csv. And the data it's 30 respondents, allegedly, who participated in a study regarding the effectiveness of 3 diet types. The variables in the data set are respondent diet group, the height in inches, and a person's weight. And diet group was a 1, 2, or 3. In theory, it's thought to be the group a person was randomly assigned to. At least that's what I read. But when you look at the data a little bit, you might go, really? They were randomly assigned? And then on top of that, there was this study was a single observations in that they just took a person's weight at the end of the study. So we're not really going to, this is really a bad story, and I apologize. I should have done more homework and found a better story for you. Ironically, when I taught a multivariate class before with Lisa, actually, I built a data set that was strikingly similar to this with a high R-squared 2, and I'm like, gosh, I need to make it look more realistic. I need to have my own data for it. Anyway. So the motivating research question is, are there differences in the final weights between the 3 diet groups, and if so, what are the nature of the differences? So here's our syntax. I can read in the data, and look, I'm trying to use ggplot. There is supposed to be our weight, our dependent variable, weight. That's the histogram of it marginally. What do you think of that? Here's my first getting to know us question. Should we see a distribution like this for weight? It's plausible. Now we got people who got some type of pile, maybe or two down here in the 100 to 170, 60 pound range. And we got some pile up here above 200. Could be possible. But speaking of this, when you're looking at this and you're saying, okay, that's our dependent variable. It's continuous, plausibly. Yeah, I've got a grouping variable here. I've got some type of control variable. I'm thinking linear model, right? That's how you want to analyze it? Stick it in a linear model? Is that how you want to start with it? Maybe? I want to predict a weight based on a group, maybe controlling for height. Is that where you go with this? Anybody?
It seems a reasonable place to start, maybe.
Yeah. Okay. Well, weight. We know that weight is sort of the thing we're interested in. So if we do a linear model, what's our assumption about weight? That's my first test for you.
So we want that to be normally distributed.
Do you? Yes. Normal is involved. Is this a plot you would expect to see? Would this be okay?
It's harder to tell since they only had the weight after
Right,
the
yeah.
experiment, but I'd be concerned maybe they sampled from 2 different populations without knowing about it.
Mm-hmm.
Or
Should-
they assigned things in a strange manner.
Yeah, possibly. Anybody else? What have you learned, or what would you try to do with data when you look at data at first and you're like, oh, what's this? Would you feel a little weird about that? Is there anything you get taught about that, or is that okay? Is this okay? I'm going to take another drink. It says Diet Coke. It's 5 o'clock somewhere, though. I'll just look at the second. Can you run a linear model on this and expect it to be okay?
I don't think so.
Don't think so. So what do you do? So hold off on the I don't think so part. But if you didn't, what have you learned to try to do to fix it?
You can try transformation.
Oh, there it is. Okay. That's what I wanted to get out. Is that what you're... So here's the interplay between it. Let's go back to what the assumption of the model is. It's normal. But the only part of the distribution that's normal, that's actually normal, that's not conditionally normal, is error. And from this, we don't have error. The model for y, which would be the weight, is conditional on the mean, right? Given a value of x, it's normal. So it's insufficient information. So I wanted to say that. That's one of the things I found when I teach. When you can't keep a job like me, and you bounce from university to university, depending on where you go, sometimes you get we got to plot the data first, and if it's not normal, transform it, and that's a bad idea. Because if you transform this, there might be a big effect that you're smushing that you lose. But the other bad idea with that is if it's not normal, or if there's some other problem with error, sure enough, we've got something we can do about it in code now. We can fix the distribution in JAGs. We can put a distribution that may be more appropriate for it, rather than having to transform the data. So I wanted to talk about that as a getting to know you step, because when I look at data like this, a couple things have to go. Number one, really know your model assumptions. There are textbooks out there that say, look at your data first and transform them. Not in a linear model, right? Residuals, you gotta look at those. There are no residuals. Anyway, am I going with what you guys? Okay, just checking. So here, does this look a little bit better? Here's the data by which diet group people are in. This is where I'm like, really? Okay. And then here's a plot of height by weight, colored by diet group. And there's your implausible data for you, right? I look at this and I'm like, okay, yeah, that looks pretty good, and that looks pretty good. And oh, in the red group, we got a little outlier here, maybe something. You know, I'm not really. This is. And I look at this, I'm like, oh yeah, that's totally a linear model. Am I right? Analysis of covariance, maybe? No? Well, what do you call it with an interaction term? That's where I was going to go with it. So, what type of analysis would you run for these models? There it is, right there. I look at this and I think, okay, I want to be able to predict weight. I need to predict it based on which group you're in. I need to control for your height. And when I control for height, because these lines aren't the same slope, there needs to be a height by group interaction where the lines are allowed to vary. That's not, I guess that's not ANCOVA. I always think of it that way. Was that cool? The other thing I've learned when I've taught in multiple places is sort of the older textbooks would be like, ANCOVA doesn't have an interaction. You need to see if that's violated. I think that's wrong too. The assumption of the model, you set the assumptions of the model going in.
Right. That's the thing. It's a more control viewpoint. You would say the variable you're controlling for, the covariate, doesn't have the same effect, right?
Mm-hmm.
But you can just make a more general model that lets you do what you want to do.
And that's where I come at it from, which is like, you know, make a model that makes sense for the data.
Just
I don't like worship at the throne of ANCOVA. It needs to have no interaction, right?
Just like homoskedasticity, like you can relax with that. So you can
Exactly.
that model.
Exactly. That might be a question on your homework next time. How would you do that? But anyway, it brought up an interesting question. Like, and this is where I'm getting to know the program, getting to know where you're thinking. But my thinking is always, you make the assumptions. But a lot of times when I grew up teaching, I was told the assumptions. You see the difference? It's the difference between taking your data and shoving it into assumptions that may not work, because you didn't. But back when those assumptions were made, they didn't have JAGs. They had some of the theory, but good luck getting it to work, right? It was very easy to do a linear model, so that's what they just made everything into it. When you what's the saying? If all you have is a hammer, all you see are nails, right? We got really good hammers now. We got really good tools. We don't need. We can specify the assumptions, and I feel like it changes our modeling approach if we do it that way. Anyway, anybody want to? I want counterpoint though. Argue, disagree. You know, it's okay. It's not a big change in thinking. This is not radically different. I just added the interaction. But I just did this with a linear model. So this is the LM function in R. I made the diet group a factor variable. So it does the dummy coding for me. I did not specify which type of coding I wanted, so it picked the first group as the reference group. And then group 2 and group 3 show up otherwise. And then in R, whenever I do a linear model, I insist on putting all the lower order terms explicitly in the model just because I want to be able to see them there in code. Mainly, it's partly because I want to know what the model is doing explicitly. You could get away with, I think, just putting height star factor in, and it would include all those in smaller syntax, but in teaching, I want to make sure it's all there, right? So here's a plot, residuals versus fitted values. Well, we got a little something going on here. There's a lot of spread in this little area that wasn't there, but otherwise, it may not be completely homoskedastic, right? May not be completely normal residuals. This is a QQ plot. Got an outlier. I think those might have been the data points we were looking at in that one group. We got other things we could look at. Residuals versus not really. We got maybe a leverage point with that one of them, but it's hard to tell. Anyway, that's what I do with it. And remember, the data it's conditional on your predicting values. Oh, there's the good old ANOVA table. Do you love those? No. But you've all taken the classes where they go away, right? Like you go like so much into a ANOVA table. That's the other thing I always comment about with how we teach things. Like I don't care about the ANOVA table very much anymore because we're about to not have one in Bayes, and there's so few analyses where this shows up. I don't like it, so I don't go much into it. If I were to teach I'd probably never teach design of experiments because you wouldn't want me doing that. And we have an expert over here who would do that. But if I were to teach other classes with ANOVA tables, I'd be like, ugh. People would be if they really wanted those ANOVA tables, they'd be very much let down.
Even in design, we stop using them when we get to random effects.
I was going to say, yeah, they go away really quickly, right? Yeah, they were great. When I taught like before I really knew the world, they were really great. And then I started knowing things. I'm like, oh, that's such a small case sliver of what we actually do. But let's look at these parameters now. Should we start to interpret? Here's another test for you. Let's talk about what this means. What does our intercept represent? Yeah, a person. What type of person does this refer to? So the intercept is the predicted value when all the predictors are 0. So that is a person who was 0 inches tall because I didn't center my data. Lisa, where you have a does not meet the assumptions. Lisa, I didn't center my data. Let's see what she says in just a moment.
We may have hear screaming from here.
Yeah, that's right. Yeah, we may hear her screaming from here. Yes. So 0 inch tall person in the reference group in diet group 1. So we would expect someone with 0 inches tall in group 1 to weigh 170 pounds.
That's amazing.
This message is held for review. Oh, let's just show it. There it is. This is kind of fun. Yeah. All right. So so we got that. We got the first one out of the way, and that was good. And we want to volunteer for this value right here. What's that represent? It is slope for the reference group. That's very good. So it's a conditional slope. So for a person who's in group 1, for every inch they are tall, their weight goes down by 0.37 pounds. Sound good? But the catch to that, this is good. That's right away. At some campuses, they don't understand the conditional main effect part. That's fantastic. Way to go. I dig it. Learning. You're my focus group. How do you feel about that? The fate of my impression of your program rests upon all of you. What about this factor variable? Anybody else want to volunteer? What does that represent?
The differences between the reference group and the second group in the intercept.
4.
Height is 0.
That's it. For a 0 inch tall person, here is the difference in weight between the reference group, 170, and this group, which would be negative 2 pounds in this group. Very good. Okay. And so then this would be the difference between the reference group and group 3. I did not explicitly ask for the difference between group 2 and group 3 on here. I probably should have. What's the word here? What's the Iowa way about multiple comparisons? I ask. I'm not trying to poke fun of this. If you've got a factor variable and we've got 3 possible means, how do you adjust p-values, or do you adjust p-values? Or they talk about that? What's the way that you learned? What's the good way?
Well, it depends on what you want to do. If you just want to do the possible mean differences, you would do like 2p, but if you're more complex, you could do
Gotcha. I asked that pointedly because in Bayes, it's all multiple comparisons. There is no group analog, like omnibus. So that starts to make you think, okay, now what do we do with it? So that's one of the big differences between the two paradigms.
I think very first week in Dr. Loe's class, I went in and talked to him and I said, the ANOVA table is stupid. We don't really care about the omnibus. We care about multiple comparisons.
And did you say, yeah? No.
Well,
No.
I say it depends.
It depends. No, you're right.
The answer he gave that I liked the most was the table is useful to help you figure out like model things.
Yeah, I get that. Yeah.
I bought that.
And if you want a kind of a blanket statement on whether you can look for multiple comparisons, right? I think that's maybe I'm saying it wrong, but I think this is where like the fun thing about getting to know each other is we all have a little bit different way of looking at models, right? And modeling things. And so I want to know what's consistent with what you're doing. I'm not trying to trick you. You've been taught a way, and I'm just trying to work with what that happens to be. And I'm certainly not going to try and insult your instructors. That's not what I'm doing either. Those are, I'm basically trying to understand where the differences lie with everything here. So, okay, finally the interaction, that's sort of the difference in slope, we can think of it as, or the difference in weight whenever height is a given value, right, for each of these. And now we're out of town. But that's good, because that leaves us with some great places to start next time. I got lots of stuff prepped. But what we're going to do is that same analysis. Right? And by the way, you all passed with flying colors. It's totally cool. But we're going to do that same analysis, but we're going to do it all in Bayes. And we're going to sort of start to look at and see if we will probably start, how are we going to start making the same inferences? How are we going to start making the same determination? And then I'm going to ask that question again. What do we do about multiple comparisons? If they're all multiple comparisons, what do we do? So I'll leave it there. Any other questions before we go? Lisa says, the p-values shown by default are not less concerning for type 1 error than those we asked for via extra syntax. Yes, agreed. That's what Lisa says. Okay.
The other thing is the way that R fit the sum of the squares, it will make a difference in the order.
Yes, that's right. The is it type 3 versus type 1 sum of squares?
Yep.
If I do the ANOVA table right here, and I did not specify which one it is, I don't remember which type this is. It also is it marginal versus conditional, right? Mm-hmm. So for the lower level ones. But one thing we can agree on, though, I think, this should be, the interaction should be the same across tables, right? Hopefully.
The thing that, if I remember, they learned is like you start over with a model with interaction.
Yeah.
And you don't get rid of interaction just because the p-value is not significant.
Yeah, that's right. I mean, because what these p-values are telling you are conditional, right? I mean, so you may end up having to have it there for certain reasons. All right, cool. Well, then for next week, if you wanted to read ahead, I'd say read chapter 6, chapter 5, kind of those two. No homework yet. I'll have a homework for next week. I got a lot of stuff prepared already for next week. I'll just keep preparing stuff just in case. You can read ahead if you'd like. We can go with there. I'll probably add some more to it because there are some things I thought about in my sleep last night. I needed to add that. Oh, I wanted to add that. So we're sort of adding on things that we're going to see throughout the rest of the analyses in class here, and this is one where we're building it. So, all right. Thanks, everybody. Good to see you. Have a great weekend, and stay warm.